Welcome to day 14 of the Advent of Code. Today is all about another virtual machine, this time with storage and interesting bit operations. So these instructions store a value at an address in memory, and the values before they are stored are manipulated by a bit mask. So these zeros in the bit mask set the value or the bit in the value to 0, the 1 set it to 1, and the x's don't influence the bits in the value before it's stored. Okay, cool. So here's our small input and our large input. And then the parsing I already prepared. Let's quickly look at it. So either we try to parse this bit mask or we try to parse this memory storage. So we will either have a string and 2 nils or a nil and 2 strings. And here I simply check for that. So sum is just the opposite of nil, literally. Okay, so if it was a bit mask, then we return a map with OR and keys. And for OR, we have to replace the x's in the bit mask with 0, because 0 is the identity of OR. We don't want to change it before passing it as a binary number. And for AND, we replace the x's with 1s, because 1 is the identity of AND. Okay, and for the second part, address and value can simply be passed as longs. Okay, so then we have to execute, and maybe let's quickly look. I compiled. Right, so that's how such a program then would look, right? Here's the bit mask changing, and here are the storage to memory. Okay, so how would we execute such a program? We've made good experiences with our nice reduce function, f value and collection. And maybe let's look at that one more time. So the collection is, of course, our program because we want to execute each instruction once. And then for the value, we need some initial state for our virtual machine. Okay, so maybe let's say we have a bit mask key that's mapped to all 0 and -1. We use 0 because initially we don't want to set any bits with OR, and we use -1, which is all ones in binary, because we don't want to clear any bits initially. Okay, and then we want a memory, which is just a map from address to value, and initially that is empty. Okay, then we have a function that takes the current state and the instruction. And since the instruction is quite involved, let's maybe immediately destructure it. So we can say the keys are OR and address value potentially, and we want to store that as instruction. So here again, either these two or these two will be present. Okay, so let's check if OR is present to see which case we have to handle. So if we have an OR, then we have one of those guys here, the bit mask change. So we can simply basically copy the new bit mask here into our state. So we want to update, we want to associate the state. The key is the bit mask and the value is our instruction. Right? I don't need update because the old value of the bit mask is not interesting. Okay, so otherwise, if we have an address and the value, what do we have to do? Maybe let's first do some destructuring. So right, so we have the state. We want to look at the bit mask, maybe like this. Okay, but we can also destructure the bit mask immediately and say those is comprised of keys OR and. Okay, that's also looking good. And then we want to update the state, this time the memory. We want to associate an address with a value, but of course we need to process the value with the OR and AND bindings, right? So maybe let's put it in the next line and say we start with a value, and then we need to bit OR the OR value, and we need to bit AND the AND value. Okay, let's see. Make it nice and tidy. Okay, at least it compiles. Let's see if we can now execute the program. Okay, memory 864,701, that looks familiar. So let's just look at the memory and then just at the values, not at the keys. Then we have 64 and 101. And if we then reduce with plus, so add them up, we get 165, and that's correct for the small input. Let's try with the large input. Yeah, 886 and 99 at the front. I think this is also correct. This looks familiar. Okay, cool. So again, reduce comes to our rescue for virtual machines. Okay, so for part 2, now the interpretation of the mask changes. It no longer influences the value, it influences the address. And how does it do that? So the zeros are now unimportant, they are ignored. The ones set the 1 bits as before, and the X's say this bit could be either 0 or 1. Try all possible combinations. So for a single X, we have to write to 2 addresses. For 2 X's, we have to write to 4 addresses. For 3, it's 8, then 4, 16, 5, 32, and so on. So that's a little more involved. Okay, so that's our new small. And then again, I prepared the parsing. Let's immediately compile. So how does it now differ? So for the OR, we replace the X with 0 because 0 is the identity element of the OR operation. And for float, what do? We replace the 1 with 0 because the ones are only interesting for the OR, right? And then we replace the X with 1, so only the X places will have a 1 in them and the rest will be 0. Okay, and of course then we have to parse, that's normal. Okay, and then I have an interesting function. Let's look at the input and output first. So the input is the number 42. 42 has 3 bits set in the binary representation, namely 2, 8, and 32. And the output is a power set, if you will, where all the combinations of those 3 bits are written down. So here none of the bits are true. Here only the 2 is true. Here only the 8 is true or set. Here both of them are set. Here only the 32, and so on. So you get 8 possible combinations. And here at the end, all of them are set. Okay, so how does this work? So let's play in our mind through the example 42. 42 is not 0, so we go to the interesting recursive case. We compute the highest 1 bit. That's a standard library function in Java. That's very handy. That says out of the bits 2, 8, and 32, 32 is the highest 1 bit. Okay, then we flip that bit 32 in our 42, and we get 10. And then we recursively compute the subset of here we recursively compute the subset of the 10 and hopefully get basically already half of our result, right? And if we have half of our result, what is left to do? We simply copy the entire result and then say, let's take every number in this temporary result and add 32 to it, or flip the bit 32, right? Then we get the second half, and then we can simply combine them with the concat, which simply fuses multiple seeks or concatenates them. Okay, and this is just an optimization of a more general power set function. That's an interesting exercise in recursion if you want to do that. Okay, cool. And just to make sure that it really works, power bit set, yeah, 0 to 810 seems to work. And for 42, it also works. Okay, cool. Then we have another helper function and our execute. Maybe let's look at the example program for this one. So let's start at the execute. Again, we use reduce fval call. We want to reduce over the program, so we get single instructions. And then the value, we can simply copy the initial state from above. That was here. Right, okay. Just so you can see the initial value on the screen, so the fill memory now should make more sense. Okay, so what do we want to do? We want to store the value at the address, but we also have to manipulate the address with the OR once, and then use these floating bits to compute all possible combinations of those being set or not set with the help of our power bit set above. Whew, okay, cool. So how would we do that? So let's start with the easy part. So the new address is simply the old address combined with the OR via bitwise OR. That was that was simple. And then let's use another reduce f value and collection. What do we want to reduce over? We want to reduce over the power bit set of float. Right? So if float is 42, here we get 8 different numbers. Okay, then the initial state for the inner reduce is simply our state. And then our function, what does it take? It takes the current state and then the bit set from the power bit set. And then we want to update the state at memory. What do we want to do at that memory cell? We want to, or at that complete memory, we want to associate an address with a value. Okay, but the address has to be still combined with that bit set that came in. And we do that by simply flipping those bits. Okay, cool. So let's clean this up a bit. It compiles. That's always reassuring. Okay, and how would we now use this down below here? Let's see. So our function for reduction in the execute, what does it take? It takes the old state and it takes an instruction. And since the instruction is quite involved, let's maybe immediately destructure it and say we have or float or we have address and value. So again, only one of those conceptual pairs will be set. Okay. And then we can do another if simply, right? We can say if sum of or, then we know we have the first case where we just have to update the bit mask. We already know how to do that. That would be associate the state at bit mask and give the instruction as the new value for the bit mask, right? So simply replace this one with a new version. Okay, and otherwise we want to fill the memory. We give state, address, and value because the function above needs it. Okay. Okay, that also compiles. So let's see if we now execute this, what happens. Okay, that's looking normal. Let's see if we now look at the memory and then at the values and then reduce via plus. If we get a familiar output, yeah, 208 looks familiar. And now if we use it with a large example, it ends in 573. Yeah, that's also correct. Okay, cool. So if you're already familiar with bit operations, this was a walk in the park, and otherwise maybe you have lots of question marks. Okay, so from a Clojure perspective, what was new today? I think I've never used sum, but I'm not quite so sure. Again, it's just the opposite of nil. Then we used the bit or, which would be spelled like this in Java, and the bit and, that would be spelled like this in Java. Maybe you've seen them, just one of them, not two. These are the bit operators and not the logical operators. And since they are used so seldomly in Clojure, they have very long-winded names. Okay, and the rest was just good old reduce, but what we saw for the first time here is nested associative destructuring. That can be quite confusing. I had to look it up on Stack Overflow because I rarely use it from day to day. Okay, cool. And then we saw that was nothing new. And then we saw here the bit XOR, which simply flips a single bit from 0 to 1 or 1 to 0. And then inside the Java standard library, there are maybe a handful of functions or a dozen functions that compute bit stuff, right? And some of that, if you're interested, is taken from the book Hacker's Delight. You can already also see that in comments in the JDK. That's an interesting book if you care about this bit stuff. Okay, and as I said, computing a general power set or a power sequence of a given sequence is a nice recursive exercise. I highly recommend you put that on your bucket list, your programming bucket list. Okay, and then here we have more nested associative destructuring and another bit XOR. The rest is not really new. Yeah. and here as well. So you see that reduce is quite powerful. Normally you say, oh, maybe I need some real state here, put them in atoms or refs or agents or whatever. But so far we didn't have to resort to that. All is computable via reduce, it seems. Okay, so that was quite a lot of code to demonstrate. So that's why I prepared a lot of stuff. I hope the amount of code doesn't grow too much, or maybe all I can show you in 10 to 20 minutes is a complete program and not write anything live. Let's see how the exercises evolve.